a piece of Yellowstone National Park just exploded. Not a trickle of lava, not a puff of smoke, but a violent, instantaneous blast. On June 13th, 2026, at 5:09 in the morning, a section of ground in Biscuit Basin tore itself open. A fissure, 18.5 meters long, fractured the earth, throwing rocks and boiling water tens of feet into the air. That is 61 feet. As of this month, the area remains closed. A new, violently spouting pool of boiling water marks the spot where solid ground used to be. But here is the detail that tells the real story. This was not a volcanic eruption. It was not driven by magma. It was powered by the one thing that makes Yellowstone a more immediate, unpredictable threat. Water. The explosion in June was a hydrothermal blast. A pocket of shallow groundwater, superheated by the volcano underneath, flashed to steam in an instant. This event did not happen in isolation. It happened just north of Black Diamond Pool, the same feature that triggered a much larger explosion on July 23, 2024. That blast was powerful enough to destroy a tourist boardwalk and hurl debris hundreds of feet. The danger at Yellowstone is not some far-off, hypothetical supereruption. It is the ground you are standing on suddenly deciding to boil. There are more than 10,000 of these hydrothermal features in the park. 500 active geysers. More than half the world's total, all simmering on a fragile lid of rock just above an immense heat source. And what happened in Biscuit Basin proves that lid can fail without any warning at all. This is the part the headlines do not capture. The greatest risk at Yellowstone is not the monster that might wake up in 1,000 years. It is the 1,000 smaller beasts that are already awake. They are hissing and steaming, and occasionally they explode. To understand what is happening, you have to understand the engine. You have to look past the steam and see the mechanism that powers it. The thing that blew a 61-foot hole in the ground last month is merely a symptom. The cause is a two-tiered magma system of almost unimaginable scale. Directly beneath the park, from 3 to 10 miles down, lies the first chamber. A reservoir of rhyolitic magma, high in silica, measuring roughly 55 miles long and 25 miles wide. It is this shallow body of heat that powers the geysers, the hot springs, the mud pots, the spectacular, violent steam explosions. All of it is driven by the heat leaking from this upper chamber. But that is not the whole story. Below that, from 12 to 30 miles deep in the Earth's crust, sits a second, much larger chamber, a reservoir of basaltic magma. In 2015, a study co-authored by University of Utah seismologist Dr. Jamie Farrell confirmed its existence. It is 4.5 times larger than the chamber above it. This is the source, the deep furnace that slowly feeds and recharges the shallower system. So you have a supervolcano built in 2 stages, a colossal deep chamber of basalt feeding a slightly smaller, but still enormous, shallow chamber of rhyolite. And it is this upper chamber that everyone is watching. Now here is the part nobody is putting on the news. That upper magma chamber is not a giant sloshing lake of fire. Hollywood has shown you a vision of a glowing molten ocean ready to burst through the surface. That is wrong. The reality, confirmed by decades of seismic data, is far more complex. Geologists describe it as a crystal mush. Imagine a frozen sponge, mostly solid rock, but with pockets of liquid magma trapped in the crystalline matrix. It is not liquid. It is a rigid, seized-up solid, holding just enough melt to be considered active. The question has always been, how much? How much of that sponge is actually wet? For years, the estimate was somewhere between 5 and 15%, not nearly enough to cause an eruption. Then, in December of 2022, everything changed. A landmark study published in the journal Science gave us the most detailed picture yet. A team led by Dr. Ross McGuire, a geology professor at the University of Illinois, used a revolutionary technique to get a new number. They did not drill. They did not set off explosives. They listened. They used supercomputers to analyze years of ambient seismic noise. The faint, ceaseless hum of the planet. Distant ocean waves crashing on the coasts, tiny micro-earthquakes from all over the world. These waves travel through the Earth, and by measuring how they slow down when passing under Yellowstone, a 3D map can be drawn. A geological CT scan using the Earth's own vibrations. The result of that scan was staggering. The new estimate for the shallow magma chamber was 16 to 20% liquid melt. Immediately the headlines wrote themselves. The amount of magma had doubled. The volcano was waking up. The risk was higher than ever. But that is a profound misreading of the data. Michael Poland, the scientist in charge of the Yellowstone Volcano Observatory, put it plainly. The amount of magma did not increase. Our ability to see it did. It was like getting a better prescription for your glasses. The object you were looking at did not change size. Your focus just got sharper. And what the sharper image revealed was not a sign of impending doom. It was the opposite. A mathematical confirmation of safety. As Dr. Poland explained, if 20% is molten, that means 80% of the magma is still solid rock. The system, in his words, is kind of seized up. It is too solid to move. It is too gridlocked to erupt. There is a rule in volcanology, a critical threshold. For magma to become eruptible, it needs to be mobile. It must reach a state where the liquid pockets connect and the whole mass can begin to move and ascend. That number is called the critical melt fraction. It sits somewhere between 35 and 50%. Yellowstone at 16 to 20% is not even halfway there. It is physically incapable of a supereruption. The crystal mush is a traffic jam, an engine with its gears frozen solid. So the greatest irony of Yellowstone is that the study everyone thought was an alarm bell was actually proof that the supervolcano is, for now, dormant, locked up. Seized. Zoom out, and the history of this place is written in scars across the American West. The current Yellowstone caldera, a massive 30 by 45 mile crater, was formed 631,000 years ago. A date that high-precision geochronology has recently refined from the older estimate of 640,000 years. During that eruption, the lava creaked tough. Ash was blasted so high into the stratosphere that it settled in layers as far away as Louisiana. You can still find its geological signature near the Mississippi River today. That event ejected more than 1,000 cubic kilometers of rock and ash, the minimum required to be classified as a V8 supereruption. But that was not the first time. It was not even the biggest. The ground beneath Yellowstone is not the source of the heat. It is just the current victim. The volcano is powered by a geological hotspot, a plume of intense heat rising from deep within the Earth's mantle. This hotspot is stationary. The North American tectonic plate, however, is not. It is drifting slowly, inexorably, to the southwest. At a rate of 4.6 centimeters per year, about the speed your fingernails grow. As the continent slides over the fixed blowtorch of the hotspot, it leaves a trail of volcanic calderas in its wake. A burn track stretching from northwestern Wyoming, back through the Snake River Plain of Idaho, all the way to its origin point near the Oregon-Nevada border 16.5 million years ago. Yellowstone is just the latest stop on a very long journey. And it has made this stop before. Roughly 1.3 million years ago, the hotspot fueled the Mesa Falls Tuff eruption. Smaller, but still catastrophic. And before that, around 2.1 million years ago, it produced one of the largest volcanic events in the planet's history. The Huckleberry Ridge Tuff eruption. A blast that formed a caldera 47 miles wide. The sheer violence of that event is difficult to comprehend. It buried thousands of square miles in superheated ash and rock, fundamentally changing the climate of the entire planet. So, we have 3 data points. 2.1 million years ago, 1.3 million years ago, and 631,000 years ago. An interval of about 800,000 years, and then an interval of about 660,000 years. This is where the most persistent myth about Yellowstone is born, the idea that it is overdue. You take the average of those two intervals, you see we are past the 600,000 year mark, and you conclude the clock is ticking. But the United States Geological Survey is clear on this point. Volcanoes do not work on a schedule. They are not beholden to alarm clocks or calendars. The average of two random intervals is a mathematically meaningless number. An eruption is triggered by physical conditions within the magma chamber, like reaching that 35% melt threshold. It is not triggered by the passage of time. The last volcanic eruption of any kind at Yellowstone was not a supereruption. It was a comparatively quiet lava flow on the Pitchstone Plateau about 0 years ago. The system is not a simple on-off switch. It can express its energy in 100 different ways, from a tiny puff of steam to a continent-altering blast. And that complex behavior is happening right now. For the last few years, scientists have been watching a bizarre anomaly on the northern rim of the caldera. A section of ground near the Norris Geyser Basin, an area roughly the size of Chicago, began to swell. The Norris uplift anomaly started in July of 2025. The ground began rising at a rate of about an inch per year. Norris is already one of the hottest, most dynamic thermal areas in the park. It is home to Steamboat Geyser, the world's tallest. And now, the ground itself was bulging upward. But then, as suddenly as it began, it stopped. By mid-January of 2026, the uplift had officially paused. As of June 2026, the USGS reports no significant net deformation in the area. The ground simply stopped rising. Dr. Michael Poland acknowledged the spectacle of it. Saying the uplift is the size of Chicago makes it sound incredibly grandiose, he said in January. But I think it's pretty stunning even if it's not particularly unusual. His final point is the most important one. That doesn't mean that the volcano is about to erupt. It's Yellowstone, being Yellowstone. The entire caldera floor is remarkably elastic. Geologists call it breathing. The ground regularly rises and falls by an inch or two a year as magma, water, and gas shift miles below. The surface inhales and exhales. From 2015 to 2020, the caldera floor actually subsided. It sank. Then the Norris uplift began. Now it has stopped. This is not the sign of a system about to fail. It is the sign of a healthy, active system doing what it has always done. It breathes. But here is the detail that changes the foundation of the story. Just as scientists were watching the ground stop moving, a new study was about to rewrite the rulebook on how the volcano works at all. For decades, the dominant theory was the mantle plume model, a relatively straightforward vertical column of hot rock rising from near the Earth's core, a blowtorch aimed straight up at the crust. But that model had problems. It did not fully explain the distribution of magma or the strange geometry of the hotspot's track. On June 27, 2026, a geodynamic study published in the journal Science by researchers at the Institute of Geology and Geophysics of the Chinese Academy of Sciences offered a new, more radical explanation. Their 3D modeling suggests it is not a straight plume at all. Instead, they propose a broad, powerful mantle wind, a massive, tilted current of hot rock being pushed horizontally beneath the western United States. This mantle wind flows from the southwest, and when it hits the subterranean wall of the subducting Farallon plate, it is forced upward. It shears off and rises, pushing diffuse pockets of magma closer to the surface, creating the Yellowstone system we see today. This is a paradigm shift. It completely reframes our understanding of the volcano's plumbing. It is not a simple Bunsen burner. It is a complex interaction of massive tectonic forces, a vast underground river of heat being deflected toward the surface. It means the experts are still, in 2026, discovering the most fundamental mechanics of how this thing even operates. The blueprint is still being drawn. This constant discovery, this rewriting of the science itself, is the heart of the Yellowstone story. We have a system so complex that our best technology is just beginning to understand its basic shape. We can now map its crystal mush chamber by listening to the hum of ocean waves half a world away. We are realizing its deep plumbing might not be a plume, but a wind. And at the same time, on the surface, that same system proves its raw power with sudden, unannounced hydrothermal explosions that can tear 61-foot fissures in the ground overnight. It is a place of immense, continent-shaping power that is currently locked solid. It is a place of immediate, localized violence, where boiling water is a far greater threat than magma. There is a dissonance between the two realities of Yellowstone. The reality of the supervolcano, the lava creek tuff, the existential threat to civilization, is a geologic story. It unfolds on a timescale of hundreds of thousands of years. It is a threat that, based on the physics of the crystal mush and the 35% rule, is not currently active. The machine is turned off. Then there is the reality of the hydrothermal system. The geysers, the hot springs, the explosions at Biscuit Basin. This is a human-scale story. It unfolds in seconds. It poses a real, tangible risk to anyone who walks across the park's thermal basins. And it requires no warning, no earthquake swarm, no ground deformation, just the right combination of heat, water, and pressure, a flash of steam. The work of the Yellowstone Volcano Observatory, the partnership between the USGS, the University of Utah, and the National Park Service, is to bridge that gap. They track every tiny earthquake, an average of 1,000 to 3,000 a year. They measure every millimeter of ground deformation with GPS. They monitor the temperature and chemical composition of the geysers. All of this data feeds into a single, overwhelming conclusion. There is no evidence of an impending eruption. The trend lines are flat. The vital signs are stable. The volcano is not building towards a catastrophe. It is in a state of background simmering. But that simmering is, itself, dangerous. The explosion in June of 2026 was not a volcanic event, but it would not have happened without the volcano. That fine distinction is likely lost on anyone who might have been standing nearby. The public imagination is captured by the supereruption, the doomsday scenario, the global volcanic winter, the end of agriculture in North America. And that is a real part of Yellowstone's past. The evidence is buried in layers of ancient ash across half the continent. But the scientific evidence says that part of the story is on hold. The present danger is quieter, more insidious. It is in the boardwalks made fragile by acidic steam. It's in the ground that looks solid, but is just a thin crust of center over boiling water. It is a constant reminder that the heat engine is just a few miles down, and even when it is not erupting, its influence is everywhere. The very beauty of the park, the geysers that draw millions of visitors, is a direct product of this immense, leashed power. Old Faithful, erupting roughly every 90 minutes, shoots 8,000 gallons of boiling water into the air. It is a spectacle. It is also a pressure release valve for a system of unimaginable energy. So 3 questions hang over the caldera tonight. When the magma beneath the park finally does begin to liquefy, when it starts the slow journey from 16% melt toward that critical 35% tipping point, will our instruments be able to give us a warning in time? How many more hydrothermal explosions like the ones in Biscuit Basin will it take before we recalibrate our fear? Moving it away from the distant supereruption and toward the immediate, unpredictable danger of steam? And what does it mean to build a society on a tectonic plate that is slowly but surely dragging itself over a stationary blowtorch that has torn the continent apart 3 times before and will inevitably tear it apart again? The North American plate continues its journey southwest. 4.6 centimeters this year. 4.6 centimeters next year, pulling the land surface slowly away from the heat source below. Deep in the mantle, The vast current of hot rock pushes upward, deflected by a sunken tectonic plate, feeding heat into a system that is 80% solid rock. For now. And on the surface, in a quiet basin in Wyoming, a newly formed 61-foot fissure of boiling waterspouts and churns, a small wound on the skin of a sleeping giant. The steam rises, the ground still breathes, and the deep crystal engine, for now, remains seized.